Okay, sorry, the 1 minute left. So I'm happy to introduce today's Sequest seminar speaker, Kevin Grossmanner. He got the PhD in Berkeley, supervised by Peter Hojaba, and recently he's working in the Leiden University Institute Lorentz. Today he will talk about numerical holography. Please start.
Okay, thanks very much, Niku, for the introduction. Wait just a second. Try to make sure I stay on time here. Yeah, yeah, thanks very much for the invitation. First of all, last week to Jeju, that was very, very nice, and to stick around for a little while longer in Korea. This is my first time in Korea, so this has been a really enjoyable experience. Okay, so the work I would talk about today has to do with holography, and I guess it's this general sort of goal or approach or of trying to apply black hole physics and having it bear on actual condensed matter systems. Let's see what conclusions we can draw for actual condensed matter systems. So today what I'll talk about are strange metals. And if that's unfamiliar to y'all, don't worry, I'll explain what strange metals are in a moment when we get there. But first I'll talk about the ADS-CFT correspondence and a little bit about the history, just in case there's the concept of holography or the ADS-CFT correspondence is not so familiar. And then we'll talk about the system that we want to apply it to, which are strange metals. And then specifically, I'll talk about the results that we have on some of the thermoelectric transport in these things called strange metals. I won't talk about everything in the paper. There's quite a lot of material that we put in this paper. But I'll talk about some of the things that I find to be the key sort of most important results. Okay, so introduction to ADS-CFT correspondence and some history. And here I thought I would give a kind of story, fairy tale kind of background to holography. So I view holography as a physics adventure, and it's in these italics font because now I'm talking about a fairy tale. So once upon a time, there lived a group of physicists who were trying to understand the mysteries of the universe. And this is a stock image of them, right here. They asked, what is the nature of space-time, or space and time? What is the ultimate theory of everything? And what happens when objects fall into a black hole? This is just a snippet of or a choice list of the kinds of questions that were asked during this call. One day, Hathoth the Wise had an idea. He said, what if everything in the universe is like a hologram? And all the information about the universe is encoded on a two-dimensional surface. This idea became known as the holographic principle. This, by the way, was one of the image generating AI's version of the holographic principle. Midjourney, I think it was. Over time, they began to see that it could explain many puzzling phenomena, such as the entropy of black holes. They realized that the information that falls into a black hole is not really lost forever, but is somehow encoded on the surface of the black hole. This was a profound realization that changed our understanding of space, time, and gravity. So I've listed here a number of the early works that sort of predated the what people tend to count as the start of ADS-CFT, which is this 1997 paper by Juan Maldacena. So it's important to note that there was quite a bit of discussion that came before Maldacena's paper about sort of a more general concept of holography that would apply generically to any theory of quantum gravity. Of course, starting from these early papers, Bekenstein, of course, had this paper of entropy of black holes and so on, but then Susskind really gave the word of hologram into this picture. And then Petter comes into the game as well, talking about holography and field theory. And then there's more talk about entropy in black holes in this context. And then finally, Maldacena comes up with the first concrete example of holography or the ADS-CFT correspondence. And at first, this took a while to kind of digest. And here's the next kind of famous paper by Whitman, which kind of digested this work by Maldacena and made it slightly more sort of understandable. Okay, but how could the universe be like a hologram on a surface? ADS-CFT, said Maldacena the Brilliant. A magical portal that connects the world of gravity and the world of quantum field theory, like a mirror reflecting one world onto the other. So one world, of course, lives on the boundary of this ADS space, called the CFT, just a particular type of field theory that has a specific type of symmetry. And those symmetries happen to match the isometries of ADS space, which is this kind of negatively curved, maximally symmetric space-time. Here denoted by this picture here, which is sort of like a simplified version of the Escher drawing of called Angels and Demons, where these are angels and demons. If you're familiar with that. At first, this idea seemed too good to be true, but as more and more physicists explored it, they found that it was incredibly powerful. They could use the ADS-CFT correspondence to study the properties of black holes, the behavior of quarks and gluons in a plasma, and the dynamics of condensed matter systems. So this is the start, sort of fairly quickly after Maldacena's example of ADS-CFT, the start of what one might consider ADS-CMP, ADS condensed matter. I think perhaps lots of people would consider this paper, this breakthrough paper by Kovtun, Son, and Starinets as the start of that, of really applying ADS CFT to condensed matter systems. This famous paper is where they first computed the famous bound for the ratio of the viscosity to entropy density. And then, as you can see, actually fairly quickly on after Maldacena's paper, Whitten, after already kind of digesting Maldacena's work, already saw that it could be applied to gauge theories, in particular to QCD. And this continues to this day. And so the elders handed down to us this magical dictionary and said, "May this fill your mind with fuss, go compute and forge ahead." So this, I should say, I've taken this dictionary, this ADS-CFT dictionary. First of all, this picture I take from Kumad. He always has this picture around in his slides. But this dictionary I take from the textbook by Jan Zanen and Kunaz Ham and their two students at the time, holographic duality and condensed matter physics. I should say this entire dictionary is sort of a result of an enormous amount of work that went into holography, starting from this sort of 1997 work by Maldacena. So this kind of important or essential factors here that translate from boundary field theory to the bulk gravity theory is the important thing is that the partition function on one side is mapped onto the partition function on the other side. Now, sort of combining that with the lore, the common lore, the usual idea that ADS-CFT is a weak, strong duality or a weak, strong relationship, wherein usually we consider the quantum field theory side to be strongly coupled and the gravity side to be weakly coupled, or meaning weakly curved. Okay. Then this picture of mapping one partition function to another partition function should seem very, very mysterious. On the one hand, the partition function for a strongly coupled quantum field theory, I mean, that would be extremely difficult to compute. But then the partition function on a very weakly coupled gravitational theory, you can imagine, should be considerably easier to compute. If it's weakly coupled or weakly curved, then I ought to be able to do something like a saddle point approximation to this partition function and simply evaluate the partition function or the integrand of the partition function onto a vacuum solution, which is roughly speaking what you do. The difficulty, I suppose, on the gravity side would be to actually solve the equations of motion. So what you would do would be to solve the equations of motion and then plug the solution into the partition function as a saddle point approximation. So there are certain assumptions that go into that. One of which is that there may be several different solutions. And if you're only summing over one solution, then you should have some general argument as to why that's the one that matters the most. Otherwise, you should really be summing over all possible solutions. But secondly, also, there's just the technical difficulty of solving Einstein's equations. Depending on how difficult the scenario is that you're trying to study, there may be all sorts of other fields in your gravitational side. And generally, solving Einstein's equations in anything more than like the simplest situation is very, very difficult. This is why I write in the title of my talk, Numerical Holography, because we, generally speaking, except for the very, very simplest cases, you're almost automatically going to be forced to do some numerics, solve Einstein's equations. The other sort of important properties are if you're interested in a scalar operator on the quantum field theory side, such as an order parameter, then unsurprisingly, what you do is you put a scalar field on the gravity side. If you're interested in something charged, or where is it over here? Well, if you have a fermion, then you put a derive. So some of this dictionary is kind of understandable. But very importantly, the energy momentum tensor is dual itself to the gravitational field. It has the correct symmetries. It's a symmetric 2 tensor. And then the other thing I said was the gauge field on one side becomes a vector on the other side. So it's very common here to see that what looks like a global symmetry in the quantum field theory side will generically be a local gauge symmetry on the gravitational side. So, any global space-time symmetry is dual to a local isometry, for example, and global internal symmetry is turned into local gauge symmetry. So, for example, if you had global U1 symmetry on the boundary, then you would have some gauge field on the gravitational side. These are sort of general lessons that we can learn. The other important things here are these statements about sources of operators and vevs of operators. So quite nicely, both of those things are packaged in essentially one single object, which is the boundary, sort of near boundary behavior of the appropriate operator, whether you're talking about a scalar operator or the graviton or a gauge field, that's specific to the situation. But what you generically do is look at what happens to this operator as you approach the boundary. The sort of leading behavior, as a leading fall-off behavior as a function of this radial direction towards the boundary, will give you the source, and then the subleading will give you the vev, both contained in the same object. And that's spelled out even more in more detail in this 1998 work by Gupser, Glavanov, and Polyakov, and by Witten. And so this is called the GKPW formalism, named after these gentlemen here. And I've just written here what you would do for scalar, in the case of the scalar field and Maxwell field and the graviton. This is, of course, spin 0, spin 1, spin 2. There are, of course, Dirac versions of this as well, spin 1 method. But I've just given these examples because these are the ones which are kind of important to our case. So let me just talk briefly about what you would do for a scalar field. So if I'm interested in the 2-point correlation function of a scalar operator, which I may be interested in on the quantum field theory side, then it turns out, and that may be extremely, extremely difficult to compute on the quantum field theory side because the quantum field theory side is strongly coupled. Okay? So in other words, if I were to compute this diagrammatically, I would have to sum over all possible loop diagrams in principle. And that's even assuming that it converges. But it turns out that you can write this expectation value as just a ratio of two functions, those functions being the vev and the source of a scalar field, in this case, a massive Klein-Gordon scalar field that you put in the bulk. Okay. And then the question there is then, how is that scalar field that you put in the bulk related to the scalar operator that you have in the boundary? And the relationship is given by this mass scaling dimension, mass scaling dimension. So that's delta is the conformal scaling dimension of the operator O, and then M is the mass of the Klein-Gordon field. And there's just some sort of relationship between the mass of the scalar field that you put in the bulk and the conformal dimension of the operator that you want in the boundary theory. So at the moment, of course, I'm not deriving any of this, but I'm just telling you the prescription. Okay. And all you do is you put a Klein-Gordon field, you solve the Klein-Gordon equation, the massive Klein-Gordon equation, in an ADS space. Okay. So box squared plus, or box plus m squared phi is equal to 0. But where that box is the box for ADS, not the box for flat space. You solve it in some coordinates, and the important thing is its behavior in the radial coordinate of ADS. And you just send this radial coordinate to infinity, and then you ask what is the behavior of this, phi as r tends to infinity. The other thing people tend to do is maybe they might compactify this dimension. They might go to like z is equal to 1 over r, and then the boundary is at z equals 0, but it's the same. So you would be asking in that case, what is the Taylor expansion or the Laurent expansion of this function phi near z equals 0. And there's going to be this sort of leading behavior r, which tends to be non-normalizable, but it will have some coefficient, and then some next to subleading or the next subleading term, and then it will have some coefficient as well. In general, you Fourier transform this, so it will have some function of k. And then all you have to do is take the ratio of those two functions. That's it. And that's the 2-point function of the scalar operator in the boundary that no one could have computed in the field theory alone. Pretty darn remarkable, ask me. Solving a
question.
Yes, please.
The A term, that is some divergent term, right? And the B is usual normalizable term. By the way, so what will determine A and the B?
What will determine them?
So what physics will fix A and the B, capital A and the capital B?
Well, so for that, it would be, let's see. This particular form of phi will be a solution to some equation. So at the end of the day, it will be a choice of what equation that phi needs to solve. We will have to solve some differential equation. And what I'm telling you is that differential is the massive Klein-Gordon.
So at the level of differential equation, capital A and the capital B is integration constant. Am I right?
I suppose you can think of it as an integration constant. I would usually think of an integration constant as a constant term here, something that scales like the r direction. That's right, it's on the r direction. So I would have usually thought of an integration constant as something that scales like r to the 0. But I suppose if you factorize a variable like r to the minus b minus 1 plus delta out of the equation, so you write phi as r to the some power times some other function, then the equation that function satisfies, then it would be an integration constant for that. Yeah. But
what you're saying is,
yeah, go ahead.
So what you're saying is that the Klein-Gordon equation will pin down A and the B?
That's right.
What does K mean here? You may not find it, but I mean, you're talking about some dependence on the space-time.
That's right. That's right. So let's say I were to do this for ADS 3. Yes. So there would be a time, there would be a radial direction r, and then there would be an extra spatial direction, in which case k would be the wave vector associated with the extra spatial direction x. So the way people often call the coordinates on ADS are the following. So you have time, then you have the radial direction, then you have what are usually called the boundary spatial directions. Okay? And the boundary spatial directions, you can either let them be on a sphere, as usually is the case for ADS, but actually for simplicity, what people tend to do is they just decompactify the sphere and just turn the sphere into flat space. So that's what I would like to do just for simplicity. It doesn't make much of a difference. So for me, the coordinates are T, R, and a whole bunch of flat directions, X, Y, Z, X1, X2, X3.
Planar black holes, is that what you're interested in?
Pardon me?
Planar black holes?
Planar black holes, if you want spherical black holes, then those X, Y, Z directions should actually be on a sphere, in which case they would be angular direction. But the distinction is not so important for me in this case. But to answer the question, what is this K? The K is the wave vector associated with the boundary directions. Okay, so A and B are determined by K and implicitly determined by M and L, but only in this particular combination. Okay, is that okay? Did that answer the question? Thanks.
Okay.
Okay, and then you would do something similar for Maxwell. So something that one might be interested in is, let's say, the conductivity of a system that has U1. So that would be related in this way to a two-point function of the current operator. So if I wanted to know the two-point function of a current operator rather than a two-point function of a scalar operator, then I would do something very similar. In the gravity side, I would add a gauge field. So on the gravity side, I have the usual sort of Einstein-Hilbert with this extra term that takes me to ADS. And then I would add an F-squared term for this extra gauge field. And then I would solve for the equation of motion for the gauge field with some gauge fixing conditions, obviously. And then I would ask the question, what does that gauge field look like as I approach the boundary? You'll have something like this. And then the prescription here is far more complicated, which is why I didn't write it down. It's not simply the ratio of these things, but nevertheless, there is a way to going from this expansion for the gauge field to the two-point function of the current operator. Okay, it's just slightly more complicated. Similarly, for the gravitational side, viscosity is related to the two-point function of the stress tensor, the energy momentum tensor. And the energy, like I said in the dictionary before, the energy momentum tensor is dual to the graviton. And so what you would do is you would just have gravity, and then you would expand this, so perturb around this background, and then ask what does that perturbation look like as you approach the boundary. So here the equation, the appropriate equation would be Einstein's equation in vacuum, except that vacuum is ADS, not physics. Okay, so the pattern here is always the same. So the moment you know what it is, you isolate what it is that you want to put into the gravity side, such as either scalar or Maxwell or just pure gravity. Then all you have to do is propagate that degree of freedom towards the boundary. And then according to what the behavior of that thing is, as it approaches the boundary, I should be able to extract from that information the appropriate two-point function that I want on the field theory side. Okay. So there's some vastly more complicated story when you're talking about three-point functions or higher point functions. You compute these using what are called Witten diagrams, but I don't need to talk about this. So for our purposes, these two-point functions are enough. Okay, so as you can see in all of these cases, and particularly if you're interested in something like shear, then you're going to have to solve for, in this case, it would be Einstein's equations in some background. Okay. And in the most general case, you will have all of these things all together. Okay. You don't just isolate one versus the other. You might require a theory that has all of them all together, in which case you would be solving for Einstein's equations with a rather non-trivial energy momentum tensor on the right-hand side. So solving that may be hard. Okay. That's where the difficulty lies. But at least that's maybe something that we can do numerically, and that's something that maybe we can trust numerically. Whereas numerical solutions, even numerical solutions of very strongly coupled systems are very hard to trust. Okay. Okay. So it's using this procedure, by the way, that Kufman, Son, and Starnets were able to compute the shear viscosity in a particular theory in this particular theory, and compute the entropy density as well, and then work out this ratio. Okay. So any questions? Before I move on. So that was the discussion of ADS.
Yeah, one question is in your previous there in the shear viscosity and the entropy density, or what is the capital N? Is it large SUN, that large N?
That's right. So yeah, I've sort of swept something under the rug here, which is that on the gravity side. So let me take, for example, Maldacen as an example, just so I have a concrete example. In that case, you have n equals 4 super Young Mills, and then supergravity on the other side. Okay. There you have an entire family of super multiplets on the gravity side. There's a large number of fields. There's a very, very large number of fields. And in fact, in principle, you ought to take the number of fields. Okay. You ought to take the number of fields to infinity. Okay. In order for am I hearing myself? In order for the duality. Okay, I think I'm hearing myself. In order for the duality to really hold, a la Maldacena, he does really have to take n goes to infinity. Okay. In principle, I think the belief is, or maybe the hope is, depending on you, what word you would like to choose, that hopefully you are able to take, to back off away from the n equals infinity limit, sort of order by order. So usually people will say, okay, a strict n equals infinity limit, then this holds. Specific relationship holds. But if n is not actually strictly infinite, then you will always have order 1 over n corrections to anything that you compute. And
could you remind me? So capital N, large capital N is in terms of the Yang-Mills theory parameter. So could you remind me in terms of the corresponding gravity number?
What is n in the case of gravity? So in this case, on the gravity side, you actually need an SUN symmetry group. So not just one. Or
I see.
Yeah, you need an SUN. I mean, part of the reason behind this, I mean, goes back actually to earlier work to Tove, where if you remember, if you calculate SUN gauge theory, SUN Yang-Mills, and you calculate the diagrams in SUN Yang-Mills, you have what are called ribbon diagrams, because it's SUN, right? So the representations of SUN have both an upper index and a lower index, and you represent them by these two lines. And then if you just draw some generic diagrams with these ribbon, wherein each line has these two lines which are directed, one going this way and the other going in the opposite direction, then some of those diagrams will be planar. If you know what I'm talking about. So I'll draw an example of a planar diagram. And this is an example of a planar diagram, just because I can draw it on the board. But then there are all sorts of other diagrams that I can't, draw on the board without the diagram crossing itself. And this is a non-planar diagram. And it just turns out that those non-planar diagrams, if you work it out, scale like inverse powers of n relative to the planar ones. And it's this kind of simplification that happens when n is infinity for SUN gauge theory that allowed the Maldacena and whatever to actually strictly show that one side is dual to the other. So technically he needed to make this approximation. Whether or not it holds at finite n, I think if you ask certain people, they probably will say no. And then some other people will say, well, maybe it approximately holds. Maybe that's good enough. Okay. And then, so whatever, maybe this relationship is good, and then it's hard to imagine that all of a sudden at finite n it's completely not good. So I would hope that maybe this relationship holds, but up to order 1/n corrections.
You are studying on lattice field theory about what large n would be, and typically anything beyond 3 is sort of large n.
Yeah, sorry, what numerically? Yeah, it's the same sort of thing that, so a good, exactly right. So a good community of people who are studying QCD, for example, study large n, what is called large n QCD. And again, it's because of these simplifications that happen to SUN gauge theory when n is large. You would say, okay, but that's not, I want to study n equals 3 for strong interactions or for QCD. But it turns out that there are large n computations apparently reproduce results in QCD very, very well. So it happens to be the case. It seems to be the case that from, in this work, n equals 3 is large enough. I don't know why, but that's just the case. Okay, let me now get to the system that we actually want to apply these ideas to. So this is called the strange metal. Generally in hole doped cuprates. So these are high TC superconductors. You can see this sort of green region here is everywhere where you have superconductor. And you can see that it goes in various, I should say the vertical axis is temperature, the horizontal axis is hole doping. Hole doping just think of it, it's a very complicated system, a whole bunch of different types of atoms in there, or sorry, elements in there. And sometimes some of them have more electrons than others, sometimes fewer electrons than others. It's actually quite similar to a semiconductor in that sense. And then depending on how many atoms I put of one type, I might have an excess of electrons, or I might have a surplus or a deficit of electrons. So I guess for hole doping, I want a deficit of electrons. And I just might put slightly more of one type of atom than the other. Okay. And depending on how many atoms of one type I put, I might have different amounts of hole doping. And that's what the horizontal axis is. So you can think of the horizontal axis as just slightly tweaking the material that you're working with. Okay. And when you do that, you end up with this rather complicated phase diagram where you have superconductivity in this region here, and then all sorts of antiferromagnetic order over here, and then a Fermi liquid over here. And let's not discuss what on earth a pseudogap is, but I want to discuss what this strange metal is.
How well are these things understood theoretically in that matter, right? Is it the cartoon plot or?
No, so this is not a cartoon plot. This is of a specific material. What I'm not entirely sure is cartoon or not are these transition regions. That is, there's a kind of overlap.
And I have a theoretical description of strange metals.
No, so we don't have a theoretical understanding of strange metals. It's not at all Fermi liquids. So there are proposals around. So one of them is, for example, something called there's no consensus.
Where do we have consensus? Non-ferromagnetic.
Yeah. This is understood. Fermi liquid is understood. Pseudogap, I think there's theories of pseudogap area. It's really the strange metal there's this huge swath of area that no one really knows what's going on. Like I said, there are proposals. There's some marginal Fermi liquids is one of them. But none of them explain all of the properties of strange metals, and neither is the thing that I will show you today. So we have some successes. We also have some failures. So we'll see.
If you were to write down a definition of strange metal, like what properties is it that?
Perhaps I'll get to it in a second.
I'd like to ask some basic terminology. ESC means the D-wave superconductor.
Yes, but this is not.
What is the AF?
Antiferromagnet.
Antiferromagnet. What is the SDW and CDW?
This one, SDW,
Yeah.
spin density wave. And none of this matters. Let me assure you, none of this matters. The only thing I'm interested in is the strange metal.
Okay.
But since the question was asked, let me talk about what the strange metal is. However, before I get to the strange metal group, perhaps I should talk about what ordinary metals look like so that we can appreciate this.
Not a strange metal case.
Right, so we can appreciate why strange metals are called strange metals. So this goes back to the work of Drude in 1900. So the idea is sort of like, it's kind of just like plain code, really. You just have balls rolling down in a potential in the presence of a whole bunch of things in the way that they can collide with. Otherwise, these electrons are free. So they just have collisions, and the collisions are Poisson random. So with some particular time constant tau, which just means that on average, there's one collision per tau worth of time, on average. And then you ask, what does the momentum of this thing look like, or of an electron in the system look like as a function of time in the presence of an electric field? So in the presence of an electric field, of course, it feels a force. If there was nothing in the way, then it would just accelerate forever. But because of all this stuff in the way, it sort of gets deflected a whole bunch of times. And then this is the kind of model for what that sort of motion looks like. And you just model it by some collision time. This here, and this relaxes the momentum. You know it relaxes the momentum because in the absence of any force, this would relax the momentum exponentially. Okay, the current is related to the velocity in this way, which is charge density multiplied by the charge. The velocity is related to the momentum in this way. This is non-relativistic stuff. Electrons moving in metals are non-relativistic. Just Fourier transform this equation, you get a relationship between electric field and electric current. The relationship is just resistivity. If we move this guy onto the other side, then that would be conductivity. So the resistivity is just given by this. Excellent. So there's some net resistivity. This is the resistivity when there's no frequency dependence at all, which means this is DC resistivity. If I were just to put a fixed electric field across this object, this is the resistivity that it would have. I can invert that to tell you what the conductivity looks like. The real part of the conductivity looks like this. The imaginary part looks like this. You could have worked, these are related to each other by Kramers-Kronig. But anyway, this is important. This is what's usually called the Drude peak. If you plotted this as a function of frequency, it would look like a Lorentzian with a half max equal to 1/tau. And you can do more things. You can add a transverse field. When you add a transverse magnetic field, then you'll have a genuinely two-dimensional resistivity and conductivity matrix, which are inverses of each other. And that also allows you to talk about the Hall effect. Okay. But I just write down here some expectations for what the temperature dependencies of resistivity should be. And the expectation is for a metal that rho should scale like temperature squared. Roughly speaking, because the number of states that at low temperatures, I should say, because I've drawn here what the Fermi Dirac distribution looks like. Of course, at 0 temperature would be a step function, but at finite temperature, it's slightly smoothed out. The width of that smooth area is about of order T. So there's of order T number of states to scatter into, and then an order T number of states to scatter out of. So you expect the resistivity to scale like T squared. And for similar arguments, because the transverse, if there's an magnetic field, the transverse process would require an extra collision. It turns out the cotangent of the Hall angle, which is defined to be this ratio of conductivities, should scale like temperature. Okay, so that's just our expectation for ordinary metals, and that's borne out in experiments with ordinary metals, up to some caveats. But now let's talk about what strange metals look like. So any theory of strange metals will have to explain this stuff because this is just experimental. So linear resistivity is almost always like the first thing that anyone talks about when they're talking about strange metals. So rho scales with temperature, not as temperature squared. So here's an example from actual data from an actual material. Where we see, okay, there's superconductivity happening here, but then and then a superconductivity transition, and then this thing is linear over an enormous range of temperatures, almost up to by the time we start getting to the point where this is going to melt. Okay. There's also something. There's more to say about this. There's something called the Mott-Joffe-Regel limit, which is where the scattering length, the electron-electron scattering length starts getting to become of order the lattice length. At that point, any more scattering will become no more resistive. So actually, the Matveev-Rego limit, the expectation, and this is what's borne out in experiment for ordinary metals, is that eventually this should taper off. This thing lasts straight through it as though this limit didn't even exist. So what is going on there? Another phenomenon that you'd have to explain is this power law in the AC conductivity. And the AC conductivity looks like this, where this is a particular experiment. And these are for different temperatures, but at some point these curves sort of just lie on top of each other, and then you get this beautiful omega to the -2/3 scaling of sigma. So this does not look anything like Rude. Rude is this Lorentzian. Okay, so what's going on here? You'd have to try to explain this. The other thing is that the Hall angle or cotangent of the Hall angle scales as t squared, not as t. So here's an example of data showing that. And then an extra thing is in experiment, what people find is even if you do have a nice Drude peak, that's that's kind of sufficiently high temperatures, even if you do have these nice Drude peaks, eventually you have a secondary peak coming around in the mid-IR. And in fact, even here where it's harder to see, this is not actually a Lorentzian. This is the superposition of a Lorentzian and a slight bump over here in the mid-IR, which you can find by simply subtracting the Lorentzian. So yeah, what is that mid-IR peak? I should say for ordinary metals, you have this Drude peak. Eventually, of course, at sufficiently high temperatures, you will eventually get another peak, but that's due to exciting cross interactions among bands. That's a much, much higher temperature that having to do with the gap between the two bands, between the valence and conduction bands. So that's not at all mid-IR. That would be thousands and thousands and thousands of mega. And then there's something more to say about this linear in T resistivity, which is that there are there are multiple regimes of scattering usually. So for example, in an ordinary metal, there's a regime where you have temperatures below the Debye temperature, between the Debye and the Matveev-Rego limit, and then above the Matveev-Rego limit, where you expect different scalings in T. So in fact, you do get linear resistivity for ordinary metals, but you don't get linear resistivity over all of the temperature range. And that's generally what you would expect. The scattering mechanisms, even in a strange metal, are very different in different temperature ranges. But why is it that the resistivity seems to be completely oblivious to this? Here's an example of a slightly different region in the phase space, where you do get these phase transitions between the superconducting range and the pseudo gap in the strange metal. And you do get these sort of regions where, okay, the superconductor, the resistivity is 0, but then you get this sort of gap in between where you have a slightly different scaling than the linear scaling that you have on the strange metal side. You expect that whenever you have phase transitions of this sort, where the scattering mechanism is very different, that you'll have different scalings in temperature. Sure enough, this region dies off as you go towards the right, where you're moving away from the pseudo gap. But even within the strange metal phase, the point is that there are regions of different, actively different mechanisms of scattering. So why is it that the linear in temperature sort of survives over such an enormous range of temperatures?
Does look like that's not, at least theoretically, is very poorly understood, correct?
Do you mean of this particular system or in general?
I mean, these are all experimental systems, right?
Yes.
Or data from experimental systems. So, and well, our theory goes back to the 1900s for ordinary metals, right?
That's right. Yeah. Yeah, and you're asking like what happened in between.
Right.
Yeah, I mean, I'm sure lots of things happened in between, but
I think what senior condensed matter theorists said was to tell you what ring would stay around for so long, it just doesn't work, right?
well, that it doesn't work. There is going to be counterexamples for sure. Yeah.
Right, there's lots and lots of materials
That won't satisfy. Yeah, for sure.
Right.
Yeah. I mean,
There's no any interest in these materials, right?
yeah, absolutely. Yeah, I suppose you could ask why you're. It's very easy to explain why you would be interested in high DC superconductors. Why you would be interested specifically in strange metals as an application, but as a physical application for anything, I'm not so sure.
It's academic.
At the moment, it would be, for me at least, academic. Of course, I would be interested in the superconductor side. I want high temperature superconductors. I think I don't need to justify that. But
Right, and are you seeing this in group rates or
Yes. It's pretty much uniformly in group rates.
But it's not there in iron based.
That's right.
You said the derive model came out 1900, and the original derive model was quantum mechanical.
The original derive model.
Yeah, and
Yeah, right, because yeah, you have to like quantize the phonon modes and so on. I remember correctly.
yeah, so the derive model we are talking here is quantum mechanical.
Yes. At least only insofar as the states are quantized. Okay, so yeah, I think maybe I can skip this because otherwise I will never get to the actual results. So let's just skip this for the time being. We can get it. Let me say what it is that we actually do. So what we'll do is, well, yeah, what we'll do is we'll break translations. So maybe I'll already actually skip this one. So because I will actually talk about the model. So
Is that motivated from condense matter?
yeah. So I think it's the following. I mean, breaking translations in all of these systems are going to be necessary one way or the other because these systems are always on a lattice. And it turns out that that's rather usually you say maybe if I'm only interested in low energy physics, the lattice is not so important. I like zoom out sufficiently far and then it doesn't matter what the lattice structure is. It turns out here that the lattice structure is very, very important because the electrons in principle are supposed to be extremely strongly coupled. So the model that, like the Drude model, and so usually what you have is a kind of dilute gas of electrons moving in some lattice of positive ions. But it's rather important that the mean free path between electrons, you know, before they're going to collide with each other is usually much larger than the lattice scale. That's not the case anymore if the electrons are extremely strongly interacting. Right? So the mean free path in that case will tend to be much smaller than the lattice scale. So you're never going to be able to just ignore the lattice. At least that's the common belief, or that's the lore. And so we say, okay, fine. If it's not fair to ignore the lattice, then let's put the lattice in. And so that's our basic plan. Like we're working with models that are essentially holographic models that essentially predate. They exist before. The only thing that we're going to do is we're going to put a periodic lattice and see what happens. I should say, let me thank the people who are involved in this work. This is Jan Zane and Konrad Scham, who are manning the helm in charge of this entire program. And these guys, Floris Baum and Nicolas Chanier, are more or less in charge of the numerics. I should say specifically Floris Baum wrote pretty much all of the code to do all of this work. And then a large slew of master students, very, very good master students we were very fortunate to have during this time. This is integrated over about 2 years. 2 years worth of work. And I should also thank specifically the computing clusters that we used to do all of this work in the Netherlands. Okay, so let's talk about the model. The model is this. It's a type of Einstein-Maxwell dilaton. Like I said, usually you will have all of these things. Indeed, we have all of these things. We have a scalar, dilaton, we have a Maxwell field, and we have the graviton. And the action is this specific thing. So this is a specific type of EMD theory. It's contained in a family of EMD theories that have Lifshitz scaling, where T and X scale with a particular dynamical critical exponent Z, and a hyperscaling violating parameter theta. Never mind what those things are. The point is that there are 2 parameters that quantify this family of EMD theories. And this particular one corresponds to taking theta equal to minus z and z to infinity. And it turns out to be the near horizon limit that's conformal to ADS2. But never mind, this is the theory.
Where do you get this scale to 3? With this
You can get rid of it. You can
Yeah.
certainly get rid of it, but then it'll just show up in all sorts of other places.
Yeah, so why do you have that?
The original model by Gupser and Rothschild, I should say this is called the Gupser-Rothschild model. The original model that they wrote down did not have the square root. But that's more or less. You can just rescale it to get rid of the square root.
Or you will not have the canonical form.
That's right. It wouldn't be. This wouldn't be
You
canonical.
shouldn't place certain word with scale root. Looks weird.
And see, if you go this top-down theory, then you have
Then
all
you
these
will not have
factors.
with scale root.
You have these weird factors hanging around. But if you're working bottom up, then
Yeah, at bottom up, of course, I do. Right. Particular
it's a good question. Where does square root of 3 come from?
That of course shows up in the coupling between the dilaton and the gauge field. So I guess what I really care about is the kind of relative scaling of the potential of the dilaton and the coupling to the gauge field. And I could put an arbitrary coefficient there, and perhaps there is an arbitrary coefficient there in this family of India theories. For one reason or another, this particular coefficient has like an extra conformal symmetry or something.
Maybe it's just in mixed by the asset equations, right? I mean, that's.
No, so I think it's this particular. I suspect that if you parameterize this, that there would be factors of z and infinity in various things that would allow it to have this type of symmetry, and then taking this particular limit takes a particular choice. The point though is that this particular theory in the family of theories has an extra symmetry, it has a conformal symmetry. So it may very well be that if that coefficient is not 1 over square root 3, that it wouldn't be conformally invariant. But I certainly haven't shown that this is conformally invariant. But I presume that that's a choice of, I mean, like I said, other people write this theory with a coefficient here not being equal to 1/2. Anyway, okay, so we have to solve Einstein's equations in this horrendous system. I'm going to look for a solution that has this particular ansatz that looks like a black hole so that I can have a temperature. So there's a horizon associated with this black hole where this blackening function vanishes. And then my job is to solve for F, G, and AT. I'm going to gauge fix AI to 0 and phi. That's some complicated couple of differential equations. I just do it. That's the part that we discretize space-time and plug this whole mess into a differential operator solver and then ask for a solution. Okay. This is and then to break translations, make this problem even harder. We add in a chemical potential where that is sort of cosine varying. So we can break translations in just in one of the directions or in both of the directions x and y, and we'll do it by adding this chemical potential. Chemical potential, of course, is just the source for the boundary source for the gauge field. And that's it. You just solve. And it turns out, for example, this is what the FTZ looks like for a particular value for the wave vector and the amplitude. If the wave vector is small compared to this chemical potential, the chemical potential sets the scale. If it's small compared to the chemical potential, then as we go from the boundary, which is right here, to the black hole horizon, which is right here, then this oscillation still gets imprinted onto the black hole horizon. But if we choose G over mu to be too large, then by the time we get to the black hole, this oscillation is gone. So just in terms of energy theory words, the boundary theory is usually thought of as the UV, and the black hole horizon is usually thought of as the IR. So this direction here going from left to right is renormalization. Okay? And this statement here is that any, for sufficiently high G over mu, any variation in the chemical potential is irrelevant, will die off. And then here it's actually always irrelevant, but hopefully if you choose a G over mu sufficiently low, then by the time you get to the horizon, you will still be able to get an imprint of that oscillation. So that answers the question why in all of the experiments or all the runs that we do, we choose G over mu to be low.
Motivational is cosine function.
I don't think it's just something that's oscillatory. You could choose whatever function that you want, which is not the constant in space.
So this resembles
It resembles a lattice. It's like a lattice potential. Maybe you would like to have something more boxy. You could try to do that. But then it would be just like harder to solve. Right? Cosine is much easier to.
how do you put this periodic function in the ball question? This is part of the ball question.
Yeah, so that will be boundary condition on the A. So the A. Yeah, so the gauge field will go towards the boundary, and it will have to have its boundary value right at the horizon will have to be mu. And then so it's a boundary condition, and then it, of course, we're solving a differential equation in the presence of some boundary conditions.
Use a bound, use the find where?
Yeah, at the boundary. That's why it's a function of x and y.
Okay, but what's G, was it in your captions? Because it looks like it's constant G, but then you.
Yeah, sorry, very sorry. So when it's like when we're just saying G over mu, we really mean mu bar according to this chain here.
Okay, so mu is relative to mu bar.
Yeah, it's like constant, the average value.
And if you work perturbatively, say in small g, or you hold this statue, or.
That's a good question. I haven't tried to solve.
You're just doing numerics.
So we're just doing it numerically. Yeah.
I mean, you could probably simplify this ansatz if you're just interested in that particular regime where G is less than mu. Well, less than mu, right?
I'm not sure. I mean, certainly if. So G is much less than mu, of course, but I don't know. Yeah, I mean, I'm not sure how to necessarily.
Depends on what it is.
Yeah, maybe it's possible.
People work with linear dimensions as well. Something.
Yeah, like I said, you can. So I want the periodic. Yeah, I want a periodic potential, so it may very well be possible to work with a square wave or a triangle wave or something like that, and it may very well be simpler. I'm not entirely sure, but in the case of numerics, doesn't really matter because all I'm doing is plugging it in and asking it to solve it. I think it might matter if you try to assume a condition which is too not continuous, then you might have some trouble. Because at the end of the day, you're always going to have to discretize this. And so if you have something which is super duper discontinuous, then it might be important whether I have a point on my lattice that is right at the discontinuity or not. Right? So if I have something that's smooth, at least I don't have to worry about that. Sorry, since I'm running out of time and I do at least want to get to the results of urgency. So right.
For future, you just trim the introduction, right?
Yeah. Yeah. Okay. So what we computed was, so we in the presence of an electric field and also in the presence of a varying temperature here. The temperature on the field theory side is related to the horizon radius. So variation in the temperature is a variation in the horizon radius. Okay, so there's going to be an induced variation in the horizon radius because there is a variation in the A potential.
So you put black hole.
Yeah, it's a black hole, but it's a black hole with a corrugated horizon. That's imprinted from this diagram. I know I wrote here FTZ, but a similar diagram holds for G for the metric components.
How do you know that black hole exists with the periodic boundary?
That's a good question. So, well, we solve for it. So we plug in an ansatz and see if there is a solution. And we get a solution, so that's fine.
And independent.
As a time-dependent ansatz. You can, of course, do this for a time-dependent ansatz. It's a little bit harder, but we certainly haven't done that. I don't know if we can say that for sure a solution exists that's not perturbative or something. At least perturbatively, you might expect that a solution exists. So let's say if I set the amplitude of the oscillation to be very small, then of course I'm back to having a constant value for the gauge field, and that we know there is a solution for that. There I can give you an analytic solution, or not me, Hoopser and Russia give you an analytic solution. So there's an analytic solution in the case where the chemical potential is constant. So you expect that if the chemical potential is just weakly oscillating, that there would also be a weakly oscillating horizon black hole.
Does it contradict any no hair theory?
Oh, hell?
No hair.
Oh, no hair, sorry. No, not as, certainly not.
All
as-
that's not the ABS, aren't they?
Yeah, so those are, I think those are, don't deal with cases like, for example, where the black hole horizon is perturbed, like as the, I mean, even in the no hair case, if I were to throw something into a black hole, for example, it would oscillate. So I don't think
there's
there's,
only pi 3 and flat face, right? So as you get to asymptotic ADS, then you know you can do what you want. Reset it off.
yeah, certainly. I'm not sure about the no hair theory in the case of ADF, but in any case, certainly having a corrugated horizon black hole is not. If that were not allowed, then you wouldn't be allowed to have ripples on a black hole when you throw something in, which you would have to do because it's a local theory, right? So if you throw something locally here, then it can't just do this. It has to that purpose. Okay, sorry, I'm really running out of time, so perhaps I should at least say what we did here. So we calculated these thermoelectric transport coefficients. Sigma I already talked about, which is conductivity, which just gives you the relationship between current and electric field. And then in the case where you also have coupling with thermal gradients, then you also have off diagonal components and you have a heat capacity as well. And then here's the plot that we get for Hoopser-Rorschach in 2 dimensions. So when towards green here is where we're really pushing the lattice. We're really making the lattice strong. And as you can see, as the lattice gets very, very strong, then sigma t becomes roughly constant, which means that sigma scales roughly like 1/t, which means resistivity scales like t. And then there are, let me skip these figures, whatever. They do what they're supposed to do, I should just say. The thermal conductivity and the kind of thermoelectric conductivity do exactly what they're supposed to do.
Can you say what the range of temperatures is? Can you translate back into the lab frame or whatever? Say this is across 300, 400 Kelvin.
No. I can.
Oh, mu is a key parameter.
Yeah, mu is a big parameter. This is why I can't do that.
Right.
All I can say though is that this is low temperature. So mu here is supposed to set the temperature scale, which I think this being 0.1 means that's much less than 1, which means if this were an ordinary metal, you would imagine mu to be set by something like de Broglie. What am I saying? And then this being much less than 1 would mean that we should be in the t² regime if this were an ordinary metal, but of course it's a strange metal and we should get t. Okay. And just for completeness, we also did this for a slightly different type of slightly different model, which is Reisner-Nordstrom. And you get a completely different type of scale.
No potential. So
Yeah, here in the Reisner-Nordstrom, there's no dilatation. So what I did say though was what was important about the linear resistivity is not only that the resistivity is linear, but that it's linear over such where in scales or regimes where you have very, very different scattering. And this is what this diagram is supposed to show. So we have this linear resistivity. Okay, this is at low values of A equals 0.15 and even A equals 1.1, which means we're still in this dark blue region. Okay, that's not quite so linear. Of course, we know that it's becoming more and more linear at large A. However, you'll see in a moment why it is that I'm showing these diagrams. But this is approximately linear at least, but it's more or less, completely oblivious to this transition between a very Drude peak, like AC conductivity, and a mid-IR peak, like AC conductivity. So you have mid-IR peak over here and Drude peak over here, but this DC resistivity, however, is more or less insensitive. If I increase A a little bit to 1.1, then I'll get a similar thing where I get linear behavior in the resistivity over on the left-hand side, we have this mid-IR peak showing up here. There's also here, we're showing a sound peak, the sound peak that would always be there because this is for on a lattice. And then what happens is that this mid-IR peak collides with the sound peak, and then you just have one peak on the right. So the scattering mechanism is quite different on the left and on the right. Even though the DC, so if you looked at AC, you would see very different physics. But if you looked at the DC here, it's more or less insensitive to this change. And this is just showing you kind of what we're seeing here. We're saying in this diagram, we're kind of seeing a hydrodynamic regime, which is just this Drude, and then a mid-IR peak regime. And then on this diagram, we're seeing a transition from a mid-IR to this incoherent, where the mid-IR peak collides with the sound peak. And the only problem, and this happens as we're increasing A, and the only problem here is that we only have a finite numeric window. So if I go to very, very extremely low temperatures, I run into numerical problems. If I go into extremely high temperatures, I run into very similar numerical problems. So I have available to me only a temperature window. And therefore, I can't really see the transition over, at any fixed A, I can't see the transition over all three possible regimes. But if I increase A, then I kind of shift my view in these three types of scattering behaviors. And the only problem is that if I were to increase A too much, then I would be completely in the incoherent regime and I wouldn't see any transition between the two. Unfortunately, it seems like that happens at relatively low A, which unfortunately is not quite where this is, not super duper linear yet. Okay. Of course, if you do go to super high A, this window itself only sits within the incoherent region. But if you could go through all the numerics over the entire range of temperatures, then you would be able to see the transition into the mid-IR peak and the hydrodynamic regime. It's just a subject of your constraints. I should say, I'll just flash this, but I just say we also did an analysis of just the modes, just the poles of the 2-point function of the current 2-point function. And we see exactly the pole structure. We have these two poles, the usual ordinary diffusive pole, which would always be there in any metal, but then an umklapp copy of that pole. So this umklapp copy is important. The only reason it's there is because we put the lattice. If it hadn't been there, then there wouldn't be an umklapp copy. And what we're saying is that that umklapp copy is the thing that really drives these different changes or these different types of scattering phenomena from something which is very Drude-like to something which is sort of mid-IR-like. What happens is that these two modes collide with each other and then they move off of the imaginary axis. So we're calling this umklapp hydro. So we do an actual hydro analysis of this, just assuming that the modes are whatever they used to be, plus umklapp copies. And then you see that the collision of these poles, the behavior of them are controlled completely by the critical exponents of the Buchs-Racha model. And that's why, and that's fixed. And therefore, that's why you get this universal linear resistivity, even though the mechanisms of scattering are very different. Okay, so as a final outline, so scorecard, how well did we do? So we found linear resistivity, great. We found a mid-IR peak, transition to a mid-IR peak, and we found it to be great. We did not find this power law in the AC conductivity, so that's a no. And that's one of the failures of this model. And so we need to work harder to try to get that. And about the Hall angle, that's work in progress. So we're putting on a magnetic field, the overall bind, and doing the analysis again. So the numerics may take a little while longer, but anyway, that's what we're doing. Yeah, and so going back to our story of ADS-CP. So the holographic principle and the ADS-CP correspondence became part of the physics fairy tale, a story of wonder, discovery, and imagination. Like all good fairy tales, it invites us to see the world in a new way, question our assumptions, and to explore the unknown. Thank you.
So please.
So if you were to rank these things for strange metals, right? Let's go back one slide, right? You know, do we have to see all of these in strange metals, or is it just a case, you know, experimentally, you always see this resistivity, and then we may not see the other things? Or...
No, at least in cuprates. So the reason why I sort of rank this highest, the linear resistivity, is actually it's actually used as a diagnostic to say when you're in the strange metal phase.
Right.
So that's really
It's maybe the easiest thing for experimentalists to see.
That's right. That's right.
Okay,
So
and what about the rest of it?
yeah, so this is as far as I know in cuprates, this is always also seen. This power law and DC conductivity is also always seen. This Hall conductivity in cuprates is also always seen. And this mid-IR peak is also always seen in the cuprates.
All these phenomena always appear together.
Always appear. And in fact, this is an incomplete list. There's a number of other things I believe that are phenomena that are always observed. I only put these because these are kind of the important ones that people tend to.
We already have a problem with point 2, right? So
yeah.
I mean, it's not like you have to, you go into the lab and you really have to play around and tune things. You have to get your grad student to work for 6 months to see, you know, to see one first, and then it takes them 6 months to see 2. Is it, or?
Yeah, no. You mean that
Are you?
So you mean that experimentally you don't have to work that hard in order to see this phenomenon? That's right. Yeah, this isn't the fine-tuning thing, unless of course you think of. I'm self-selecting the cuprates. So obviously, if you think of high-DC superconductors as a whole,
That's a large class, right? So
that's right. The cuprates is a large class. So within the family of cuprates, you don't have to work hard to see this behavior. So yeah, it's a bit sad or problematic, if you will, that it seems so hard to come up with a theory that would incorporate all of these things, because it doesn't seem hard experimentally to.
what about theoretically, right? If we that's matter what's going there. You mean how are they doing?
And that's better, not using blogger.
Right.
Yeah. That's a good question. So I can tell you, so I myself am not a condensed matter theorist, so I don't know all of the theories that people put forward to try to explain strange metals. But I do know one thing that, for example, I tried to put forward a long time ago, which was also unsuccessful, which was the following idea. If you have electrons interacting with phonons, the usual electron-phonon interactions in metals, in addition to electron-electron interactions, then you'll get the usual ordinary metal behavior. If you make one assumption, which is that the phonons are, for some reason, have a dispersion relation which is not linear. So they usually have omega equals k. That in fact is kind of part of the definition of a phonon.
Right.
So in other words, if it's not that, you would hardly call it a phonon. But suppose it were some other degree of freedom, I don't know what it is, but suppose there were some degree of freedom in these solids that somehow has a dispersion relation that goes like omega equals k squared or omega equals k, whatever it is, and also interacts with the electron in a fairly similar manner, like in a Yukawa type interaction, then you can show that you can get linear resistivity. But you can also you also don't get this, and you also don't get this, and you certainly don't get this.
So I guess you need to show us is basically, you know, some model from, you know, theoretical to that matter, you know, is yes.
Yeah, that doesn't exist.
It doesn't exist. Okay.
Yeah,
Holography do you some way out?
that's a good question. No, at the moment I don't have any idea to come up with this. I'm only doing this mostly because I can be more or less brainless.
Right, it's easier, right?
It's easier. I agree. You could. I'm perfectly happy to take the criticism. Like, why would you even bother to try to do this if you already do?
No, I don't do. There's nothing. There's not something out there that is yes, 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 right?
Yeah, in the absence of any better thing, then why not?
Exactly, right, why not? It's certainly curious.
So how can you see the stability of bulk relational solutions in your setup?
I mean,
Yeah, so that's right. So that's a good question. So I mean, in some sense, I've taken it as an input, right? Because I've assumed I'm solving time independent case.
Yeah,
Of course.
It's stable because
That's right, yeah.
you want the stable, yeah.
Yeah, I understand. So of course, in principle, what you should really do is, well, do a at least perturbative stability analysis, which I admit we haven't done yet. Okay, so solving these equations in a time-dependent situation is very hard. I mean, solving it even in this case is very hard. It took us 2 years on these supercomputers to do this. Okay, it couldn't have been faster. I mean, it wasn't like 2 years of nonstop. We had to get to this point. Okay, and so maybe it would be possible, but with the current numerics techniques that we have, with the code that we've written down, that I can't do that. But it may be possible to do some kind of semi-analytics.
I think it's not fine though, right? I mean, if you want to compare to experiments, it's fine. Why would you need a time dependent system?
Yeah,
Your experiment just goes in there and set up their lab and.
yeah, well, I suppose you could just say, well, if imagine, let's see how this might fail. Just play devil's advocate. So suppose I were to do a time-dependent analysis, where just put a small time dependence on the gravitational side, and then I found that actually the solution decays. Let's say it decays over a time scale which is very, very fast. Well, then it would be hard to understand how it. I mean, if it's supposed to model the strange model sits there for a while. It's not like all of a sudden not.
However, you fine tune it, so it lasts.
But yeah, then of course, then you run into a fine tuning problem. Right. Yeah.
I think it's okay, right? You have a brother, yeah, to fine tune.
Well, it's okay. It's up to you. You're okay with it. Fine tuning.
you have done cosmology for a long time. You have done cosmology for a long time.
Right, no, I think it's fine, I have a greater appreciation for what experiment is doing now, right? But it doesn't always say that. I can see how you would get over that problem. Any technical questions? So if you got a technical question.
Don't ask about the numerics.
A numerical question, maybe one.
No question, then let's thank Kevin.
You're at Leiden, right? Are the people at Leiden studying strange patterns?
It's this group. So Kornatzham and Yelzana.
Like, are experimentalists who go to their lab?
Oh, experimentalists, not in Leiden, but in Amsterdam with like Eric van Humen. Right. Yes, they are. Certainly. Then in terms of results, so we tend to communicate quite a lot with Nigel Hussey. So he does experiments. He's an experimentalist.
Okay.
But not locally specifically.
Yeah, it's nice to see these talks by experimentalists on straight patterns, right? You see the other side of what happens, right?
Yeah,
And then they get into their, lab. And, but here's my setup.
yeah, and